Okay, we've got two quick questions here on intermolecular forces. So these are both basically the same thing about IMFs. Remember IMFs, there are three basic kinds: London, then dipole-dipole, and hydrogen bonding. Now, for a molecule of a given size, so if we're compared two molecules that are similar in size, the strength increases as we go down this list. Okay, so London forces are the weakest, dipole-dipole interactions are moderately strong. Hydrogen bonding is a particularly strong version of dipole-dipole interactions. But remember, this only matters if molecules are roughly the same size. If you have something like water that has lots of hydrogen bonding, but some big, large molecule of like some wax or something like that that has a much higher molar mass than water. The London forces are actually going to dominate in that particular case because London forces get bigger as the molecule gets bigger. But as a general rule, for the same size molecules, the strength of London forces is less than that of dipole-dipole interactions, which is less than a significant number of hydrogen bonding. So this first question says we want to rank the following substances by boiling point. Sorry, this is an I, not an L, so that's boiling point. And we want to go from highest to lowest. So what we do is we look at each one of these and ask ourselves what kind of forces are present in these things. All right, so the first thing we have to do that is we have to identify what kinds of molecules that we're talking about. In this case, NaCl, we're talking about an ionic compound. Here we just have an element, a diatomic element. And then here we have both of these are just molecules. So these are molecular compounds, this is a diatomic element, and this is an ionic compound. And so what kinds of things are present in these? Well, ionic compounds have ionic bonding. So in this list, this is a list of intermolecular forces, but then way underneath this is ionic bonds. They're much stronger. Ionic bonding is much stronger than the van der Waals forces. So we can see right away that sodium chloride, because it's held together by ionic bonds, is going to have a much higher boiling point, a much stronger attractive force between the particles than these things that are built out of molecules. Okay, so our highest boiling point we expect to be that of sodium chloride. So sodium chloride is going to be larger. Now let's look at these three. And what we're going to do is identify the strongest intermolecular force in each one of these. So here we have hydrogen. Well, what is hydrogen? Hydrogen is a element that looks like this, H single bonded H. It is not polar, and therefore the only thing it has is London forces. So we can put that here, London forces. Actually, what I want to do is erase that. So hydrogen falls kind of in the London forces part of this list. And then we have C2H4. You need to review how to draw these Lewis structures if you don't remember, but I'm going to go ahead and give it to you here. And this is ethene, and this is the molecule. Now, if you'll notice this, it's perfectly symmetrical. So even though these bonds are polar, they cancel each other out. So this side of the molecule looks exactly like this side of the molecule. There's not one side of the molecule that's going to have more electrons on it than the other. So this is nonpolar, which means it also goes in this category, C2H4. Okay. And then finally we have methanol, and methanol is CH3O H. Now, oxygen is more electronegative than carbon and more electronegative than hydrogen, so this is a polar molecule. Unlike these first two examples, this is not symmetrical, and so it doesn't cancel itself out, so this is a polar molecule. Furthermore, we have oxygen directly attached to the hydrogen here, and that is a prerequisite for hydrogen bonding. So methanol will hydrogen bond. So we can put methanol on the list here, HCH3OH, as part of the list for hydrogen bonding. So we can see right away that methanol has a stronger intermolecular force than either hydrogen or ethene. So we can put as the next highest thing on our list methanol CH3OH. And then we have to compare these two. So we have to look at hydrogen and ethene and ask ourselves which one has the stronger London forces. So they both only have dispersion London forces, but London forces get bigger as molecules get bigger. The molar mass of hydrogen is 2, and the molar mass of ethene is, what is that, about 28, something like that. So this is a much, much larger molecule than the hydrogen molecule is. And because of that, the London forces for ethene are much stronger than the London forces in hydrogen. So the next highest boiling point we would expect to be C2H4. And finally, the weakest or the lowest boiling point we expect to be hydrogen. And the boiling point of hydrogen is about 4 Kelvin, something like that. It's way, way down there. So it's a very, very, very low boiling point for hydrogen. So this is the correct order. And basically what we're really doing, even though it says rank by boiling point, what we're really doing is ranking by decreasing IMFs, decreasing intermolecular forces. Okay? The second part of the problem here is, this is practice problem 15.4, is just I look at these 4 different compounds and determine which ones contain hydrogen bonding. And so this is really easy. Remember, hydrogen bonding involves a nitrogen, an oxygen, or a fluorine being directly bonded to a hydrogen. So if we don't have this present in our molecules, then we by definition cannot have hydrogen bonding. So even though this is hydrogen, and even though there's bonds in the hydrogen, hydrogen's not directly attached, covalently attached to nitrogen, oxygen, or fluorine, so no hydrogen bonding here. This molecule contains both hydrogen and oxygen, but not oxygen covalently bound to hydrogen. There is no HO bond here. The O is double bonded to carbon. The H is single bonded to carbon. This one does not have hydrogen bonding. Here we have hydrogen covalently bound to fluorine, which is exactly what we said we needed to have. So this does have hydrogen bonding. Remember, the hydrogen bonding is not this bond. That's not the hydrogen bonding. The hydrogen bond is between the hydrogen of one molecule and the fluorine of a second molecule. But that's what the hydrogen, this does exhibit, in fact, hydrogen bonding. And the last one here, we have hydrogens attached to carbon. That doesn't work. Carbon and oxygen with no hydrogen, that doesn't work. But here, oxygen directly attached to hydrogen, and so this meets that part of our criteria. So this one also hydrogen bonds. So the last 2 we expect to exhibit hydrogen bonding. The first 2 we do not.